And with that, all right, so here's a capacitor circuit where I have two switches, switch 1 and switch 2. And we're going to begin this problem with with no capacitors being charged at the start of this problem. In the problem, or in our discussion, we will close switch 1. Now, it might not be clear to you, but when you close switch 1, you create a potential difference from here to here, which is going to allow capacitor 1 and capacitor 2 to draw a charge from the battery. Here's what I'm going to ask this question that I don't get answers to. Does everybody understand what I just said?
Yes.
Okay. I like a solid no. That means, you're either not listening or don't understand. And I generally believe in you to not understand as opposed to not listening. So when I close switch 1, I complete a pathway that allows capacitor 1 and capacitor 2 to be connected to the potential difference. Even though a capacitor is technically an open circuit, we treat capacitors as if they are circuit elements where there is a closed loop from one side of our battery to the next. This should allow the transfer of charge from the bottom plate of capacitor 2 to the top plate of capacitor 1, which is going to push charges on the intermediate plates between capacitor 1 and 2. So technically, what that will mean is I will acquire a positive charge here and a negative charge there, which will drive electrons this way to create a negative charge there and a positive charge there. Everybody follow that line of reasoning? All right. But capacitor 3 is not involved. Now, yesterday, I tried to give you a reasoned argument that, based on merely the concept of what's the concept I want to use here? Conservation of charge. That there's a finite amount of charge in a circuit. I tried to trace the path of a single electron, saying that if I plucked a single electron from this plate and placed it on this plate, which is what the battery could do, then it would allow for the motion of only one charge between here and here, one electron. That once I move that one electron, the electric field would stabilize and I would have two charged capacitors. But by nature of them being in series, they would have to be brought to the same charge. That there couldn't be a difference in the amount of charges on the capacitors in series, because there'd be no way to have, and let's go ahead and just blow this up. There'd be no way to move more charge from this plate than this plate. Right? They're inside there. They're isolated. So I can't have plus 3 electrons there and minus 4 electrons there. I'm saying minus 4 electrons, that makes it positively charged. And positive 3 electrons makes that one negatively charged. I can't do that. Where'd the other electron go? Right? I can't subtract 4 electrons from here and only add 3 here. That's why the capacitors in series all have to have the same charge. Because there's no way to have a different amount of charge due to this isolated piece in the middle. Now that, of course, means that the electric fields inside these two capacitors will be different in order to equalize the charge. It also means, in the macroscopic, the electric potential on these capacitors is going to be different. It's going to do whatever necessary so that we have the same amount of charge on both capacitors. If you need a big takeaway here of what was important that I said just now, it's that capacitors in series must have the same charge on each capacitor. Must. No other rule is more important right now than that one when it comes to capacitors in series. Yes, sir?
Is this amount of charge the same as the amount that the battery has?
It's the same as the amount of charge moved by the battery, which has to be for the same reason. The battery can't push 5 electrons this way, but only bring in 4 electrons from here. There's a finite amount of charge, and the charges can't bunch up someplace and spread out someplace else. So the battery moves a finite amount of charge, and it has to be equal on both sides of the battery. I see your hand. I'm trying to complete my question, or my answer. So go ahead.
Can you repeat the statement about the capacitors and sections?
They must have the same charge. You're welcome. So, yesterday we talked about this closed circuit. And what I tried to convince you of is that the amount of charge that gets distributed is going to be related to the applied potential and the size of each of these capacitors. But we didn't actually make it to the end of that discussion. In that discussion, we only talked about what it would take to replace C1 and C2 with a single capacitance which I called C total. So what would we have to do if we wanted to replace it with one capacitor? What would be the size of that capacitance? And we use Kirchhoff's rules to show that the size of that capacitance would have to be the sum of the inverses inverted. I wrote it different yesterday, but it's not any different than that. Just a reminder that you have to add the inverses and then invert the answer. You guys remember all that from yesterday? We sure? Yep.
And this would be the same if they're given to like C1000, would be the same. Like if there was many more capacitors.
Sure. You could write this as so it could be any number. I could have 50 in a row or 1,000 in a row. You'd still just keep adding the inverses, but then invert the answer. Now, what they're going to attempt to do is ask not about this question all the way. They'll ask that as part A. But part B through D is going to be what happens to the system when they close this switch. Or what happens to the system when they open this switch and then close this switch afterwards? Those are the kinds of questions that we're going to get. And they are not obvious or easy. Those are the interesting ones, though, and they're the ones that we can set up in the lab, which I'm starting to set some stuff up here because I want you to see this. But we really need to explore the concept of what it means to have capacitors in series and what it means to have capacitors in parallel, and work the problem the way it's intended to be worked. So yesterday, I had a circuit with some values in it. Two capacitors, right? And I'm not sure what I said the voltage was for the system. Did I not give it a voltage? Just V of T. And I said one of these was 2 farads, and the other one was 3 farads. Okay. So I'm just trying to use some nice integer numbers. Let's go ahead and say that this is a 10 volt power supply. right? So I'd like to find out the charge and voltage on each capacitor. This is what we would consider to be a basic circuit problem. And it can be figured out using something called stepwise reduction, something you're going to hear a couple times this year. Stepwise reduction is a process of trying to build a simpler circuit from a complex circuit. And it involves a set of rules. I already gave you one of the rules you're going to need, which is recognition that this system can be simplified by replacing it with what's called an equivalent capacitance. An equivalent capacitance is a single capacitor that behaves electronically the same as my system of capacitors. For capacitors in series, we've been able to show that my equivalent capacitance is equal to the sum of the inverses. We got common denominators, added the two fractions together, found that they equal 5/6, but then recognized that the equivalent capacitance was 6/5, which meant the capacitance was 1.2 farads. So the total capacitance goes down when you have capacitors in series. That might not make a lot of sense to some of you, but let's remember. Parallel plate capacitors are related to the surface area and the separation distance. Do you kind of see that by putting capacitors in series, you're effectively making the separation distance bigger? There's more gap between the top plate of the first capacitor and the bottom plate of the second capacitor, right? Because I'm effectively making the gap longer between the capacitors. That's why the capacitance goes down. The manner in which it goes down, well, that's unusual. This is sum of the inverses, but we're going to see this actually sum of inverses a couple different times. This is just the first. But now that we have this, what we really have is a 10-volt battery connected to a 1.2 farad capacitor. You should be able to tell me how much charge is on the capacitor. That's just C times V. Which I think is 12 coulombs. Correct? Any questions here? You good, Carlos? Well, follow me. This is an equivalent system, but that's not the actual system. The system had two capacitors. But these two capacitors have to have the same charge on them. So if this capacitor had 12 coulombs, that means each of these must be 12 coulombs of charge. The battery doesn't know the difference in the system. The battery was presented with 1.2 farads of capacitance. It will respond by supplying 12 coulombs of charge. It doesn't know that there was actually two capacitors there. It provides charge based on the total capacitance that was connected between its terminals. But since capacitors in series have to have the same charge, it must be 12 coulombs on each. But now that we know the capacitance and we know the individual charge on each, we could use this to figure out the voltage across each capacitor, which is clearly not going to be the same. Voltage is charge divided by capacitance. So 12 divided by 2 means 6 volts here. And 12 divided by 3 means 4 volts here. So the smaller capacitor takes more of the voltage. Now, it should not surprise you that there's a total of 10 volts of potential difference across the series of capacitors. There has to be. The sum of the voltage drops in our circuit has to be 0. So I increase in voltage. When I go across the battery by 10 volts, I have to decrease in voltage when I go across the capacitors by 10 volts. Do you see that okay? I need you to. Interestingly enough, keep this in mind, the smaller capacitor gets more of the voltage. Why? It takes more voltage to get to the same charge because it's a smaller capacitor. It's harder to charge up, so it needs more voltage to get to the same charge as the larger capacitor does. So they don't share the voltage evenly. They take as much of the voltage as is necessary for them to have an equal amount of charge. That probably means all sorts of stuff, like the electric field in those capacitors probably isn't the same. It's probably different in order to ensure we get the same amount of charge. How are we doing so far? All right. So, a common twist on this kind of problem is to have an air-gapped capacitor with a space like this. And they might even be nice enough to give us the value for D and the value for A. And say you have an ideal capacitor like that. And then they have a solid piece of metal that's as wide as the plates. And they're going to take that and slide it between the plates and ask you what's going to happen to your system. And you're going to see this problem and flip out. I promise you. Every time it happens, kids flip out. But I don't want you to, because if they're putting a conductor between the plates, then what they're really doing is just slipping a wire between the 2 plates and adding 2 plates to the capacitor. What they're really doing is changing this into 2 capacitors in series. They want to throw you, but there's no reason to be thrown. This is all they've done. And the reason should be easy to understand. They put a conductor in the middle, which means they put a place inside the capacitor that has no electric field. Can't contribute to the potential difference, so you have to reorganize your circuit to match the new scenario. That's a very likely thing for them to do. So just be aware, they're just creating 2 capacitors that are in series. Now treat them like they're in series. Yes, sir?
If the conductor was like exactly, like if it was deep, like wide, like it would touch like capacitors, would it just act like a wire and like
Yep.
capacitor? Like the
Yeah, we just allow charge to flow then. Mm-hmm.
Would they say that the little like metal, the piece of metal is like almost a thickness D, or?
They wouldn't do that problem because it's too easy. Because the moment you do that, you just lose the capacitor. They'll have an air gap on either side. Now, it seems not too surprising that we should probably look at this circuit. If we look at one where we have them in series, having them in parallel seems like an appropriate next move. Now, you should draw this into your notes, but note that I'm going to change this in just a second. So scribble down a quick picture so that you can see something real quick. Ready? Can I change it?
No.
Hurry. If I can draw it this fast, you should be able to draw it faster. You're young and you're spry, and I am old and feeble. That's all the time you get. I've not changed anything. This is the same as it was. Put that in your notes for those of you who don't see why that's true. For those of you who see why that's true, don't bother. You're going to get it. For those of you who don't see it, you should understand that the wires themselves, the way the wires are, they have no electrical part in these circuits except to connect things together. So don't be confused by the wires. This circuit shows that the split in the wire occurred here. But that is electrically equivalent to having a split in the wire there. So this too is the same circuit I drew before. What is important is that there's 3 possible loops through this circuit. There's this loop. That's a possible loop through this circuit. That is a pathway from one side of the battery to the other. There's this loop. That is a possible loop. It is a pathway from one side of the battery to the other. That's a loop. It doesn't have to include the battery to be a potential loop in your circuit. So in using Kirchhoff's rules, there are multiple ways to go through this circuit. Now consider Kirchhoff's rules for a minute. The sum of the potential drops across any closed loop has to be 0. Well, minus and plus, if I go in the direction of the red arrow, my applied voltage is going to have an increase in voltage as I go from the negative plate to the positive plate. If this is capacitor 1, I think we can all agree that this has to be the positive plate and this has to be the negative plate. There's going to be a drop of voltage of V1 as I go from the positive plate to the negative plate. So according to the red loop, V minus V1 has to equal 0. Green loop. All right, green loop's a little bit harder, but not really. In the green loop, I also have an increase in potential as I go across the battery, because I'm going from the negative side to the positive side. When I get over to that capacitor, which we'll go ahead and call a C2, it's going to have a positive charge here and a negative charge here. The drop across that capacitor has to be equal to V2. So in that loop, V minus V2 has to equal 0. So can we all see that V has to equal V1 and V2? Right? If V1 is equal to V and V2 is equal to V, then V1 has to be equal to V2. Transitive property. So capacitors in parallel, which is what this is called, capacitors in parallel all must have the same voltage. Capacitors in parallel all must have the same voltage. I hope that's not a huge surprise. They're all more or less individually connected to the capacitor. To the battery. In fact, you might not believe this, but that's the same circuit. I know you don't like that, but it is. It's electrically equivalent in that both capacitors have a direct connection to the battery. They did here too. You guys all okay with this? Now I'm going deliberately slow. If you need me to, I can pick up the pace, but I feel like this is probably appropriate. Because I'm hoping you guys realize now, if Q equals C times V, then this is going to be Q1, which equals C1 times V. And this is going to be Q2, which is going to be C2 times V. Which means the battery had to push out a total charge of Q1 plus Q2. The battery had to push out that much charge. It had to push out the amount of charge required by capacitor 1 and the amount of charge required by capacitor 2. So, the total charge has to be equal to whatever the total capacitance is times V. What is the equivalent capacitance for capacitors in parallel? When you have capacitors in parallel, the total capacitance of the system is the sum of the individual capacitors. That shouldn't be a big deal. If you go back to this, doesn't it look like we've just added more area to the system? Do you see why it looks like there's more area? Not more separation distance. We kept the separation distance the same. We just tacked on more plates, so more area. What does that mean for us? Well, let's consider our simple circuit from the moment before. If we have a 10-volt source and a 2 farad capacitor and a 3 farad capacitor, it would have an equivalent capacitance of 5 farads. Just add them together, which means a total charge of 2 coulombs. It's not true, but I'm seeing if anybody's paying attention. Is anybody really paying attention? How many would it actually be? I erased all the equations.
Wait, wouldn't it be 6/5?
No. Aw. I was hoping for more. First, C total has to be C1 plus C2. That's still 2 plus 3. That's 5. And Q equals C times V. So if the voltage was 10 and total capacitance is 5, then the charge had to be 50 coulombs. So there's 50 coulombs of charge on that capacitor. Does that track? Well, the charge on this capacitor had to be C times V. And the charge on this capacitor had to be C times V. 20 plus 30 equals 50. That seems to track. Now, so far we're just looking at simple systems of capacitors. Of course, I did two basic problems. Two capacitors in series, two capacitors in parallel. Unlikely to be what's actually on your test, but any questions so far? Gabby has one. She's trying to raise her arm. I'm not sure she's actually going to do it or not. Makes me crazy when she sits here like this, like we're in some weird limbo. Just either poop or get off the pot. What's your question?
Well, it was because we were only doing two, but if you were to have like a set of like multiple capacitors like all together, but they were in like, let's say it was like a 2x6, and you're like.
2 by 6. I'm not sure what the hell you're talking about now.
Like, okay, so you see how he has the two boxes? And then you just, you know.
So, more boxes below. I'm not
So,
sure.
Like an opening or like a parallel below it as well. Yeah.
Like that?
But then it also connects.
Just start with something like this. This would just be the sum of these three.
Right.
I know you say right. How about I'll go at my pace.
Okay.
Everybody okay so far? So, how about now? I don't mean this in a let's like gamble kind of way. I mean this in a, how about this one is, let's go with, you get the numbers right. Let's go with, these are all 3 farad capacitors. And this one is a 9 farad capacitor. And I put 9 volts on the battery. Let's solve this circuit. All right. Now, the biggest thing about this is understanding what's in parallel and what's in series. There's an intentionality to create a system where it might be difficult for you to figure that out. This is one of them. And don't be fooled. Consider always redrawing your circuit in such a way as to benefit you as to understanding what's in series and what's in parallel. And the way I would do that is let's try and put the battery all on one side, and then let's trace the line until we reach our first circuit element or junction and make this point, which I'll call point A, this point here, point A. I can do whatever I want with the wires. So I am going to make the wires a little bit longer to aid me seeing what's happening. Do you notice at point A, the wire splits into 3 wires? I see it splitting into 3 wires, but doing so slowly. There's a split, there's a split. But the result is 3 wires. C1, C2, C3. Imagine you are a train of electrons going through the circuit. Well, some of the electrons can split here and go to C1, the other ones head on to C2 and C3. And then some of them split here to go to C2, while others carry on to C3. That's no different than this. It's just that splitting all happens in the same place. Electrically, they're the same. I'll notice that they all come back together before going through C4. So, bring them all back together and then travel through C4. And then from C4, we go back to our battery. Can you now tell what's in series and what's in parallel? Stepwise reduction means taking something that is in series or parallel only and replacing it with something equivalent. Stepwise reduction. So I have 3 of them in parallel. I add them together. This one's got to be 9 farads because they're all 3 farads. Now I have something smaller. It's in series. I can reduce it in my next step. You see what I mean by stepwise reduction? It takes some practice, but if this was also 9, then 1 over 9 plus 1 over 9 is 2 over 9. The inverse of that is 4.5 farads. This would be considered the equivalent circuit. All right. Again, this represents capacitors in series and capacitors in parallel and how we reduce them for their equivalent capacitance. And I want to remind you that we have to deal with how capacitance deals with potential. We'll do the same thing for resistors and inductors, and how capacitors deal with energy, and we'll do something similar for resistors and inductors. So let's see how we can stepwise reduction to solve a simple capacitor circuit. And I gave one yesterday kind of in passing as you guys left. I'm going to do something similar today with a bit of a difference. And instead of having you try and figure out how to arrange it, I'm going to draw it in such a way that you should be able to figure out the arrangement. All right. So here is a system that has a total of 5 capacitors, a bank of 3 and a bank of 2. And I want you to figure out the following things. I would like the charge on each capacitor. And I would like the potential across each capacitor. And I would like the equivalent capacitance of the system. Now, just quick FYI, this question doesn't show up on the AP exam, but you'll have to do this to answer the questions that show up on the AP exam. So we will have to be able to do this, but this specific question, they wouldn't do this. They would fold this into something else. So this is kind of a basic idea that will get folded in and used on other questions. So again, stepwise reduction. So we really hadn't had a chance to do one of these yesterday, and I don't know that I want to count on all of you to be able to figure it out, but in order to use stepwise reduction, you have to have a clear set of either parallel capacitors or series capacitors. Now this one, there are 2 clear sets. There's a clear set of parallel capacitors here, and there's a clear set of parallel capacitors here. Does everybody understand? Now, we generally work from the inside outwards. So the fact that this system is in series with this system means we can't deal with those individually yet. We have to wait until we found the equivalent for each parallel system. So what I'm suggesting is we're going to take this and have a stepped reduction where we reduce the top to one capacitance and the bottom to a different capacitance. And this will represent one step in our reduction of our circuit. The top appears to have 3 capacitors in parallel. For parallel capacitors, we merely add them together. So that produces a total of 6 farads for my top system of capacitors. That is the equivalent capacitance for that system. The bottom system, similar, they're in parallel, I add them. So 2 and 1 gives me 3. And I still have my 10 volts applied to it. So what I've done is I've taken my system of capacitors and I've reduced it by one step into something simpler. Still, don't know if this tells me very much, but it gets me a reduced circuit, something that might be easier to deal with. Questions about our first step? All right, so our second step is to now deal with this circuit as if it is our starting point and seeing if we can reduce it. I hope you see the same way I do, that these appear to be in series. And because they are in series, my stepped reduction should be able to produce a single equivalent capacitance for the 2 capacitors in series. But because they're in series, I have to use the sum of the inverses. So this will be 1 over C equals 1 over 6 plus 1 over 3. I don't expect this to happen, but back when I used to teach honors physics and AP physics, I almost always found a student who couldn't add fractions together. I'm suspecting that that's not true here, that I won't see anybody say that this is 2/9. But I have seen that before. And coincidentally, that's how you add your test scores together, right? When we do our tests, we always have a quick little fraction. That's because those aren't actual fractions. Those are point totals for your test. So when I add these together, I would not add the tops and the bottoms. I would get common denominators, because that's how you actually add fractions in nature. So this is 2/6 plus 1/6. This is also not the answer. The answer is not 1/2 either. The answer for the total is 2 farads. It's the inverse of the answer. So 1 over C equals 3 over 6, so C equals 2. This is our reduced circuit, and this is our equivalent capacitance, 2 farads. So this whole system here could have been done with just one of those capacitors. Now, why would you have such a complicated system? Because it's quite possible you wanted to divide up the charge so that you didn't want any of these capacitors to have too much charge. Or, more likely, these capacitors might have had a voltage limit and you couldn't exceed a certain amount of voltage, but you still needed to store the equivalent energy that you needed for a 2 farad capacitor. So you would try and create a circuit here that would keep your capacitors under the voltage limit. You see, unfortunately, most capacitors don't have air between them. They have a dielectric between them. Dielectrics, unfortunately, have the capacity to break down sooner than air would, which allows a spark to pass through the dielectric, setting the dielectric on fire or destroying the dielectric or destroying the capacitor. So every capacitor that you're ever going to use is going to have a voltage limit. So you have to stay beneath it. Otherwise, the device fails. Now, what we're going to do next is completing the our process of the thing we're going to do next is completing the analysis of our circuit. by working backwards to figure out charge and voltage. Yes, sir?
On the exam, are we ever gonna have to like recreate a circuit? Like if there's one like the one on the far left, will we ever have to like recreate one?
Like from scratch?
No, like they give us like they said they gave us the one on the left, but not the same one, and the access. Will they ever ask us to like recreate a simpler one?
Yes. They've gone as far as to say you have a handful of these capacitors, create a circuit that will do this. And you'll have to draw a circuit diagram of how you would connect up the circuit to do the process you've been asked to do. It's unusual for them to do it, but they've done it. So it's not so unusual I wouldn't expect it. It's more likely they're going to do something different that we're going to try and get to today. But until we can do this, we really can't move on to more interesting examples. So let's apply this rule to our circuit. What we want to figure out is what is the voltage and charge on each circuit element. And the only way to do that with the knowledge you guys have is to work backwards from here. What I mean by that is we have a function here which can tell us how much charge is stored on this capacitor. We have a 2 farad capacitor that has been connected to a 10 volt source, so 20 coulombs of charge is stored on the equivalent capacitance. However, that's not really what's happening. We know that the charge is being stored separately on multiple capacitors. So what we're going to do is step backwards through our circuit. And we're going to apply a couple of rules. And although I've told you these rules, we've not used them in this way. The first rule is that capacitors in series must all have the same charge. So when I step backwards from my single capacitor to my system, I now know that each of these must have 20 coulombs of charge. Capacitors in series must have the same charge. I would write that on this arrow, except that I can't write that small. But that's the rule we're applying. Every time we step back, we're going to apply one of 2 rules. This is the first rule. Now, once we have stepped back, we apply this function again. We apply the definition of capacitance to figure out the voltage on the capacitor. Remember, our job was to figure out the charge and voltage on each capacitor in our system. So when I step back, I'm going to use Q equals CV to figure out the voltage, or more importantly, C equals Q, V equals Q over C to figure out each voltage. So I step back in the first one, I get 20 divided by 6. So that's got to be 10/3 volts. And the next one is going to be 20 divided by 3, so 20/3 volts. And I'm going to check my work. The whole thing has to equal 10 volts. So 10/3 plus 20/3 is 30/3, and that's 10 volts. I'm checking that because this loop must have a voltage drop of 0 across the whole loop. Kirchhoff's laws still must be maintained. Good so far? Go ahead.
I was going to ask you a question, but then no question.
You sure?
Yes.
All right. We have now completed the analysis of this intermediate step. So we're going to step back again. When we step back this time, we are going from a capacitor to a system of capacitors in parallel. So when we step back to a series, we applied the charge to each capacitor, but capacitors in parallel have the same voltage. So when I step back, I have to take the voltage with me and apply it to each capacitor in parallel. So 20/3 volts here and 20/3 volts there. And on the top, they're all the same. So each one of them sees 10/3 volts. I'm not going to write it on top of each one of those because I don't have the room. But you should have the room. So it's applied. I can write it. There. All right, so we step back and recognize that now this is our actual circuit. We have the voltage and capacitance for each circuit element. Our final task is to figure out the charge on each element, which comes back to Q equals C times V. Yes, sir.
Did you say that capacitors in parallel must have the same voltage?
I did say that.
Thank you.
So now I take the capacitance, multiply by the voltage. That gets me the charge on each of these. So we'll focus here. And 1 times 20 thirds is 20 thirds coulombs. 2 times 20 thirds is 40 thirds coulombs. We good? So 10 thirds times 2 is going to be 20 thirds coulombs. And 2 times 10 thirds is 20 thirds coulombs. And 2 times 10 thirds is 20 thirds coulombs. So I have found the charge and potential on each capacitor in my circuit. This is the process of stepwise reduction applied to a ridiculously stupid circuit. But it's effective in showing us the difference between series and parallel. Would you be asked to do this on the actual AP exam? Yeah, but not like this. They would not give you this kind of complicated circuit. They'd probably give you something with a simple series and a parallel element. So you would have to be able to do a little bit of reduction, but not something this involved, because they're going to ask other questions. So the real thing now is, does this seem simple enough where one time is good, or is this something where maybe we should take another run through it just to make sure? You sure? I say that, then I give a quiz and I get disappointed. So, tell you what, I kind of believe you, but this next one is for you to do on your own. I will give a short timer for this because I'm going to make it not particularly hard. Everybody see it okay? Let's go with 5 to 10 minutes to tell me the equivalent capacitance and Q and V for each capacitor. I have an 18-volt source connected to this system of capacitors. Does anybody have to see how it's done? Nobody needs to see how it's done? Does anybody need to see how it's done? All right. Stepwise reduction. I'm only going to draw the capacitors during this part. So my first reduction will be the right side of the circuit because they are the most inside elements. They are in series, so I need to reduce them first. So I'm not going to touch that 6 farad. I have 2 that are in series. I must use the sum of the inverses, 1/4 plus 1/12. Common denominators is going to give you 4/12. Inverted gives you 3. So this comes out to be 3 farads. Do I need to write that out or am I good? All right, next reduction is just to add these 2 together to get a single capacitance, which is going to be 9 farads. 9 farads with 18 volts applied is going to produce, I think, 162 coulombs of charge. Didn't actually have to do that. To be honest with you, I didn't have to reduce it down except that you were asked to find the equivalent capacitance for the whole circuit. Because both sides here are in parallel, they both have 18 volts applied to them. So I could have treated them individually. And when I do, I get 3 times 18 here for a total of 54 coulombs, and 6 times 18 gives me my 108 coulombs. This capacitor is done because that's the original capacitor from the first part of the circuit. So I can actually write that this is 18 volts and 108 coulombs. I will point out that the 108 plus 54 should equal the 162. It's a way to check your work. But you don't add all 3 of those together. You just add those 2. Because when we go from here to here, we're going to take that 54 and apply it to both. So don't think that we're actually storing 108 plus 54 plus 54 coulombs of charge. Those capacitors in series don't actually get 108 coulombs of total charge moved to them. They get 54 coulombs of charge taken off this plate and deposited on this plate. So just be careful. It's not 54 plus 54 on the right side for total charge. On the other hand, when I do step back and put the 54 in place, I can use that to figure out the voltage. I get 13.5 volts plus 4.5 volts. And I'll point out that if I looked at this loop through the circuit, I get a total voltage drop of 0. Positive 18 minus 13.5 minus 4.5 gives me 0. So there are tons of ways to check your work. Kirchhoff's laws always must be maintained. Use Kirchhoff's laws to check your work. All right, systems of capacitors. Let's see how they're actually going to ask us this question. If it's going to show up on the exam in this form, it'll be on the multiple choice. It won't be a FRQ, which means, keep that in mind, multiple choice, minute and 12 seconds or so per question. So you need to nail this kind of stuff pretty quick. Generally, they give numbers that are easy to use. You'll notice these numbers all worked out with no fractions, except for 13.5 and 4.5. It doesn't have to be like that. In the wild, it would not be like this. So keep in mind that we try to do this to see if you can do the process, but we know you have a calculator, so they don't have to do it this way. The one thing you have to understand about systems of capacitor circuits is they very seldom give us just that. They tend to want to change it up a bit. They'll give us a system of resistor circuit to solve. That'll be on the multiple choice. They'll give us this, One of the more likely scenarios has to do with understanding what's maintained, charge or voltage, in dynamic situations. So, this is not uncommon. And this is a little bit of a stretch because generally they throw a resistor in here and try and do some RC stuff too, but we'll keep it all capacitors for right now. And the nice thing about this is if they're all capacitors, then the circuit's charged almost instantly when the switch is closed. So at this moment, switch 2, switch 1, all uncharged capacitors. So switch 1 is closed. Find the charge and voltage across each capacitor when switch 1 alone is closed, and label the positive and negative sides of the capacitors. This one you should do, no trouble, should be quick. So only switch 1 is closed.
What's the question?
I want you to find charge and voltage for each capacitor, and I want you to label the positive and negative side of each capacitor. Okay? So 12 coulombs on each. Total capacitance was 2 farads. 2 times 6 is 12. And capacitors in series have the same charge. Is that all right so far? And then, of course, 12 divided by 4, 3 volts, 3 volts. Positive, negative, positive, negative. Good so far? Okay, switch 1 is now opened back up. These are capacitors. Because switch 1 is opened back up, the capacitors are isolated. They maintain 12 coulombs of charge and individually 3 volts of potential difference. If I could cut this wire in the middle, I could separate these 2 capacitors out and use them elsewhere. We're going to keep them together for a moment. And I want you to consider what happens when switch 2 is closed. Now, these are not batteries. Meaning, although at this moment, there is a potential difference of 6 volts from, I'll call this point A to point B in the circuit. The 6 volts is only there because the individual capacitors each have a certain amount of charge on them. When I close switch 2, the charge isn't going to stay there. There's going to be a movement of charged particles in this circuit. Something's going to drive the motion of those charges. Mostly, I've got all of these electrons all stuck in this same place. They're going to repel each other, and because of that, they're going to be pushed out of the wire and towards that other capacitor. Similarly, the fact that this side of the capacitor is missing charges, it's going to pull electrons from the top of this capacitor to try and equalize. So what wins? What drives this process? So in this circumstance, this is an interesting circumstance. At least I hope it's interesting. There's going to be a movement of charged particles until the potential across A and B stabilizes. Now, to understand what I mean by that, there's going to be a movement of charges until the potential difference from here to here is the same across the two that are in series and the one by itself. Because right now, there's 0 potential on this side, and there's 6 volts of potential on this side. So the energy that we have stored due to this is going to now be shared until both sides come to the same potential. Now, that makes for an interesting question. One that we might not be suited right now to figure out, but is what we're going to have to do next. Yes, sir?
Why aren't particles being moved when switch is open? It's like, wouldn't the bottom of the 1 farad capacitor still, like, get the electrons even if the switch is open?
No, believe it or not, because the capacitor plates aren't both exposed to the potential difference or both exposed to the other capacitors, it's as if this whole thing doesn't exist, even though only one part of the circuit has a switch on it. And the best way I can explain that is that a capacitor really doesn't exist unless both plates are engaged. And by opening up the top, we're not engaging the top plate. And so it's not a capacitor yet. You're welcome. So this is a situation in which you have to know one little tiny thing about this, or you can't do any of it. And that thing is that what drives this process, what drives the motion of charges, is the fact that both sides of this new parallel system have to have the same potential across the capacitors. What's hard to know is which capacitor is dominating this process. And I'm going to be really frank with you. When they ask questions like this, one of the best ways to help yourself is to ignore what came before and be prepared to deal with a new situation. So I'm getting rid of what was there before. I'm recognizing, too, something else, a new reality, that electrons can leave this plate, but if they do, that's going to make this plate negative. And electrons might be pulled out of this plate, and if they are, it's going to make this plate positive. This is important. Kirchhoff's law still has to work, so that the sum of the voltage drops in my new loop has to be 0. So although I do not know what the new potential is going to be, I know that V1, V2, and V3 all have to sum to be 0. Now, when I arrange this based on the direction of my arrows, I would do this as V1 plus V2 minus V3 equals 0. That will have to be true because I'm going from the negative to the positive plates. So we'll pick this up tomorrow, but this is the first kind of problem you're going to see that's like this. Once you've seen this once or twice, they all are the same. I hope you would agree that